Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already subscribed to this channel, just pause right now and hit the subscribe button. We have been looking at generative adversarial networks for the past few videos. In fact, we started off by looking at the plain vanilla GAN. And then we realized, okay, maybe we can condition the latent space so we can actually generate images of our choice. So we started looking at conditional GANs, and again, a basic conditional GAN where we supply the class labels. And then we also looked at a few applications of these conditional GANs like pix-to-pix and cycle GAN, and we even looked at super resolution GAN in the last couple of videos. We are going back to basics in this video. In fact, if you haven't watched the previous videos, I definitely recommend watching them. But for this video, hopefully you don't, this is not dependent on any of the work that we have done before, but I still recommend you watch those. Okay, so here we are going to construct a regular plain vanilla GAN. So if you have watched the previous video, it should make it a bit easy for you to follow. So we're going to construct a plain GAN, and we're going to train that on a whole bunch of human faces, different ages, genders and all that stuff. And we are going to play with the latent vector space. By the way, how do we generate images? We are going to use the trained generator from the GAN, right? And the input to that is a latent vector. In our case, we're going to fix the size of that vector to about size of 100. So some random numbers, 100 of these in a vector that goes into the generator, and the generator generates the face. Now that latent space, we don't know much about it. We don't know if that vector is going to generate a male face or a face with glasses or a baby face or what. We don't know that. But in this exercise, we are going to explore that latent space. Basically, we are going to generate, let's say, 100 images. And then say, okay, I'm going to take like these faces that look like a smiling man, and these faces that look like a neutral man's face, and then a few other faces that look like baby faces, and then we're going to just do some latent vector arithmetic. So once we identify those faces, we just are going to go ahead and take those vectors and do some arithmetic. Here in this example, a smiling man minus neutral man is basically smiling, right? The vector corresponding to smile. Now you add that smile to a neutral baby's face, you hopefully get a smiling baby's face. So that's the idea here. So let's go ahead and look at a couple of slides and jump into the code. So first of all, if you plot the latent space, for example, you generate a vector of values between, I don't know, -3 to 3, and plot them, they're all over the place. Now you don't know which one corresponds to what. I mean, this is hard to interpret. And this is not just linear like I'm showing here. The latent space is highly curved, right? So we don't know what corresponds to what. You can do conditioning, but then we're talking about the plain vanilla GAN right now. So there are many dimensions. Like if you look at most of the faces databases, it comes with appropriate tags, whether it's a man or a woman or an older man, older woman, like with their age, and are they smiling, are they angry, do they have glasses, what skin tone do they have, and a whole bunch of attributes. So how do you map that here? Like, for example, you can have a small area right here of vectors. By the way, we're talking about all vectors, right? So a small area of these vectors where it captures the information about babies. Or when you use these vectors as inputs, you generate baby faces or kids. And then when you move in this direction, you may be moving in a direction where these vectors give you female faces. And if you go the other direction, you may be getting more male-looking faces. And if you keep going, it could be older men. Again, this is just completely hypothetical, okay? And if you move somewhere down here, maybe there is like beard vectors that represent beard, and maybe the vectors that represent the glasses, and then maybe older women. And of course, you have many, many other things, like smiling, skin tones, and so on. So how do we work with this? So the latent space, we can exploit this. So how do we do that? And by the way, like I already mentioned, this latent space is highly curved. It's non-linear. I'm just showing this for easy graphic illustration. So let's say we only, first of all, when you go from, for example, something that generates babies to older men, as you move the latent vector, you may be generating, obviously you'll be starting with baby faces and then slowly moving towards men and older men. You can see this transition going from one to the other, and one way you can achieve that is get a latent vector here and get another latent vector right there, and then just interpolate 10 different values between here to generate 10 different faces. In this case, this is 5 different values. So you can do the other way around. Obviously, you can go from here all the way to older women, so you can just see the transition right there. So this is one way, but again, you do not know which one corresponds to babies, which one corresponds to older men, unless you condition this with that type of class information. Or you can just generate, like I said, hundreds of images and then get a whole bunch of baby faces and get an average. That gives you a good idea of where that the mean of that latent vector space resides, which is what we're going to do today. And if you go from women to the smiling, you can always again generate a face and gradually add smile to that face. Yeah, when you go here. So for today, let's go ahead and look at, again, this example where you have like neutral baby face, neutral man, and smiling man. So we're going to generate 10 images from, using random latent vectors. Not 10, actually. To find 10 neutral baby faces, we may have to generate 100 images, right? So let's generate tens of images and then identify many images corresponding to whatever classes we are interested in. And this could be like baby faces, man, and someone with a smile. And average these latent vectors, because all of these, they have latent vectors. The assumption is they're all very close by. And again, this is, we are again assuming that this is linear, but maybe that's not a bad assumption within a given class. Yeah, so we're averaging all of these latent vectors, all these latent vectors, all these latent vectors, and then we are performing an arithmetic like I showed you in the welcome screen, which is a smiling man minus remove the smile by getting the vector for a neutral man's face and add whatever that remaining smile is to the neutral baby, so you can get a smiling baby face. So that's the plan. Let's jump into the code. And a couple of notes here. First of all, I am working on TensorFlow version 2.4.1 and Keras 2.4.3. And dataset wise, you can click on this link. I'll share that as part of the description. And again, it's also part of the code, which I'm going to share with you anyhow on my GitHub page. And if you actually go to that link, you'll get here, which is UTK face dataset. And this one actually has a whole bunch of faces right there. And it's tagged with, although I'm not using the class labels here, but it is tagged with age and all that. I'm just using the faces, that's it. And this one, the dataset I have, if I go down here, UTK face, you can see that these are all cropped faces that I have. So if I go anywhere, so these are all ready to be used. But if you, for whatever reason, if you think, okay, this is not a good dataset or fun dataset for you, you can always go to the Celeb A dataset. So go ahead and search for celebrity face dataset, and then you can download the Celeb A dataset. And in fact, I'll probably leave the link for that to extract faces, and the data I got is from Kaggle. Right from here, and this is a large data set. Yeah, not that huge, 1 gigabyte, and it has 92,000 images. The only thing is, some of these are smaller faces, some of these are zoomed in, some of these are not zoomed in. Like if you just randomly go somewhere, you can see a whole full face covering this picture. So you may have to extract faces in either way. So the way I approached this was, do I have it? Yeah. The way I approached it was actually use the face detection classifier. And if you watched my Raspberry Pi videos where we did the face emotion detection, that's pretty much the framework that I'm using right here. So I'm using these Cascade Classifier from OpenCV. So if again, I'll probably leave the link for this one. If you go to these classifiers, again, OpenCV guys, I mean, they have a whole bunch of these pre-trained models, and I'm going to use the face one. Yeah, so frontal face, which one am I using here? Yeah, Haarcascade frontal face default XML. So go ahead and find that, download it. So using that, you can go ahead and read one file after the other. That's exactly what I'm doing here. And detect the face using our classifier, face cascade classifier right there. So face cascade detects the faces and gives you the coordinates for the face. And then we are going to use those coordinates and just extract that part of the image. So you have your full color image. I'm using the coordinates and just extracting the array from the face. And once you do that, of course, we are going to resize it to whatever the desired size. So if you're putting together a network for 256, which is probably a bit too big, you can just go ahead and resize them to 128 by 128, for example, and then save it on your local directory. That's exactly how I went from all those images to these images right here, where I only have faces. Okay, this makes it a bit easy. Again, I haven't tried it without just cropping, but this makes it a bit easy for us to work with these images. Okay, so I think that's enough background information. And now let's go ahead and see how we can train it. This is, again, a plain vanilla GAN. No modifications, not, I mean, this should be pretty straightforward. And then, well, let's go ahead and predict. That's the plan. So let's look at the GAN itself. So GAN has a discriminator, a generator, and then you combine them into a GAN, and then you train the discriminator, and then you train the generator via the GAN. So let's see the parts of it. All of these are helper functions. So let's go ahead and run these. Again, don't worry, I have already trained it, because training a GAN is the slowest part. This will take hours and hours, although I did 100 epochs, I believe, and it took, I think, about 8 hours or so on my system, even with the GPU. And the discriminator, remember, the key with any GAN is the discriminator is taking an image. It's just a binary classifier. So all it needs to do is take an image and then output a binary probability value using a sigmoid activation function. That's what we are doing right here, using the sigmoid. So we are, and we want our input images to be 128 by 128 by 3. And if you're limited by GPU or something, go ahead and try 64 by 64, or but then it's tough to see facial features on smaller images. Okay, so our discriminator input is 128 by 128 by 3, and we are gradually going from that to 64 by 64, 32, 16, 8 by 8, and eventually we are going to flatten out, and then dense layer 1 with the sigmoid activation. And we are going to use Adam optimizer and binary cross entropy loss. This is our classic binary classifier, right? So let's go ahead and run these lines. And just to see how the structure looks like, we can assign this to a temporary file right there, and then go ahead and print this. So you can see how it's going from 128, 128, our input of 128 by 128 by 1, and we are adding 128 of these filters initially. So that's what this is, and we are gradually going down all the way to binary. This is, again, our classic. And remember this number, 8192, dense layers, because 8192 came out of 8 by 8 by 128. Remember that for now. And by the way, you can just go ahead. Let's plot this. Why not? Show shapes equals to true. Yeah. Let's go ahead and plot the model. So you can just see the model right there. Or I think I saved it. Generate faces. There you go. Discriminator model. So this is our model. We are going from 128 by 128 by 3 all the way down slowly, eventually to 1 output. Okay, couple of ways to look at this. Now we need to define a generator. So our generator should generate images. Images of what size? Images of the size that go into our discriminator, which is 128 by 128 by 3. So we have to start with a vector of size, whatever the latent size vector we define, and then go all the way to the size of our image. And how do we do that? Well, let's go ahead and provide our latent dimension as input, which is, let's say, a vector of size 100. And then we add a dense layer with enough nodes that gives us eventually to get to 128 by 128 by 3. And what is enough nodes? Well, the only thing that logically makes sense is 8 by 8 by 8, 8, 128, as you can see here. 8, 8, 128. When you multiply 8, 8, and 128, you get 8192. So it makes sense for us to start right there and almost replicate this backwards. So that's exactly what we are doing here. So number of nodes, 128 times 8 times 8, which is 8192 nodes. And we add a dense layer with that many nodes. And then we slowly, obviously we are reshaping here to convert our one dimension dense vector into 2 dimension right here. 8 by 8 by 128, and we slowly up convolve or con 2D transpose to an eventual size of 128 by 128 by 3. So just play with this. If you are working with different size images, just play with these numbers, and it's not that difficult. So let's go ahead and print these so you can see how it works. So do we have generator model? Yeah, there you go. So our generator starts with a vector of size 100, right? So this is the input vector we are supplying, and then we have a dense layer that takes this 100 and converts that into 8192, and then we are reshaping it to 8 by 8 by 128, and we are gradually increasing the dimensions to 16 by 16, 32 by 32, and all the way down to 128 by 128 by 3. This is just basic putting together your neural network. Okay, now that you know this part, let's go ahead and define our GAN, where we combine our discriminator and the generator part. So how do you do that? First, you set your discriminator to be non-trainable, because we are training discriminator separately, and then we are holding the discriminator constant, and we are generating a new image. Why? Because we want to supply to that generated image to this discriminator, so it can discriminate this image as either true or fake. Okay, so that's why we are making the discriminator model non-trainable. And then we are using sequential method to add our generator and discriminator. Remember, this discriminator is non-trainable, and only generator is trainable as part of this GAN. And again, we are using binary cross entropy and Adam optimizer and so on. So let's go ahead, and if you want to look at the summary, this should be a pretty short one right there. You have one right there, input as 128 by 128 by 3. And the output is going to be binary, which is either true or false, right? So that's exactly what our GAN is supposed to do. Our discriminator is supposed to do here. Okay, so we're slowly getting there. Again, this is stuff that I have covered as part of our basic GAN, but again, reinforcing the message is always a good idea. Now let's define some helper functions that give us the information while we are training. That gives us the data while we are training. So first of all, how do you train your discriminator? You provide a real sample and then real label. Real sample, real label is 1. Fake sample, the label is 0. So we have to generate this information. So first of all, how do you get real samples? Well, we have our data set of all these real samples. So you just randomly get an image from these real samples and then assign that as X. And your Y is basically, like I just mentioned, is nothing but 1. So your real sample is 1, right? So that's what you have right there. So this is a function to generate or to supply, to fetch real images. Now you need a function to fetch fake images. And for fake images, you use generator to generate fake images. And what does generator take as input? A latent vector. So first we need to generate latent points. Yeah. So that's what this function does. So once you have the latent point generated, again, it's nothing but a vector or a bunch of vectors of size 100 in our case. That's it. And once you generate that, that goes in latent points as the input to your generator. That's exactly what we're doing. Generator model dot predict your input, and then this is a fake image. So now my X is a fake image, and the label for that is going to be zeros because this is a fake image. So let's go ahead and run this function. And again, another function to save the plots as you're training. So it makes sense for you to, for example, generate a bunch of fake images as you're training, like once every 10 epochs, for example, so you can see how the model is evolving. So that's basically this save plot function does. And finally, now we have to train the model, but then while you're training the model, it also makes sense for you to summarize certain, how your model is performing. We care about, first of all, one thing that kind of gives us a good information is discriminator model, and is it actually doing a good job or bad job. So here what we're doing is we are generating real samples, and then we are calculating using our discriminator model to evaluate the performance. Because we know this is real, it's supposed to be, label is supposed to be 1. So all we are trying to do is take the discriminator model and evaluate on your X real and Y real and report what the accuracy is. We are doing exactly the same for the fake images. So here I'm printing out the accuracy for real and accuracy for fake of our discriminator. And then we are also saving the model as a H5 file right there. Sorry about that. We are saving the model every few epochs. It can be 10 epochs, 20 epochs, whatever you define. So that's exactly what summarize the performance function does. And finally, we are going to train the generator and discriminator. So this is just not just model.fit. You have to actually enumerate manually the epochs and batches. So it takes in your generator model, discriminator model, the GAN, which is the combined model, and your data set and your latent dimensions, which is our vector, and you define number of epochs and what the batch size is. All of these as inputs, and then it performs the following. Let's look at this. So first of all, you define your batch. And let's say your batch size is 16. In that case, we are going to take half of the batch size, which is 8 images, real images, and 8 fake images, and train the discriminator. That's what half batch is there for. Okay, once you do that, then for each epoch, you do the following. And for each batch, you do the following. We're going to generate real images. Well, not generate, we are fetching real images, right? So that's what generate real images does. So from the data set, get some random real images, X and Y equals to 1 for real images, and then train the discriminator. That's what we're doing. We are training the discriminator on real images, and then we are training the discriminator on fake images. And we are training the GAN or generator via GAN, first by generating latent points, and then that is your X values, and your Y values, while you're training this, is going to be 1, because even on the fake images. This is because we want to fool the discriminator into thinking that this is a real image. Yeah, so that's what we are trying to do here. We are training the GAN, and we are printing out the values after every epoch. And of course, we are summarizing the performance. So that's what my function for training actually does. And going down here, I am actually loading the data and then training it. So I'll just go through this quickly, and then we can jump on to the predict part, which is the more fun part for this exercise. So importing the required libraries, and I worked only with 20,000 images. I say only, even that took a lot of time. And I said only because I don't think that's the entire data set. My entire data set has 23,000. In fact, I could have actually just used 23,000. I just imported 20,000 images. In fact, I first worked with 2,000 and it looked horrible. 20,000 slightly better. And each image 128 by 128. So here all I'm doing is loading these images and then resizing them to 128 by 128 in case you haven't already done so. Yeah, that's what I'm doing, and capturing that as part of my data set. And then I'm normalizing or standardizing these to values between -1 and 1, right? You subtract because my pixel values go from 0 to 255. So if you subtract -127 and divide by 127, it ranges from -1 to 1. Why -1 to 1? Because our generator, if you look at our generator uses, if I can find it, that's a GAN. Our generator uses activation function of tan h. That means it's generating images with pixel values between -1 and 1. So it only makes sense for us to normalize all of our images to between -1 to 1. That's what this does. And my latent dimension, I fixed it to 100. So it gives me a vector of size 100. And then I define my discriminator, generator, GAN, and then I just train it. So I did this for 100 epochs. Now I have a trained model. This is the fun part. So now let's go ahead and use the saved trained model and go ahead and do some sort of an arithmetic. So first, let's start by understanding exactly what type of images we're getting when we generate them. So let's start from scratch. I do not have anything in the Variable Explorer, so that's good. So let's go ahead and run these libraries. And this function is very similar to the one that you saw earlier, which is generate latent points. All it's doing is it's just giving me how many of our latent points I ask it to supply. So that's the function that generates latent points. And let's also define a function that just plots a whole bunch of images, because we are going to, for example, generate 100 latent points, which means we have to plot 100 images in 10 by 10 format, for example. So that's what this plot does. And now let's go ahead and load the model. Yeah, so we are loading this. Let me make sure 128 by 128, 100 epochs. Yeah, let's go ahead and load this model. And it's fine. It's giving me a warning that it's not compiled. We are not further training it. We are just loading it to generate new images. So now let's go ahead and generate 25 latent points, right? So generate latent points, latent dimension, number of samples. Yeah. So let's go ahead and generate 25 latent points. So if you look at your latent points right there, you have an array of 25 by 100. So you have 25 vectors, each 100 size. And let's use those to predict. All we need to do is model.predict, right? So we already loaded our generator model. And now let's go ahead and predict by supplying these latent points. So it's going to give us 25 images, each of size 128 by 128 by 3. So let's see, our X right there is 25 images, 128 by 128 by 3, with pixel values going from -1 to 1. So we need to convert those to pixel values between 0 to 1 so our PyPlot can understand exactly how to interpret these. So let's go ahead and convert our X to values between 0 and 1. And now let's go ahead and use this function to generate a plot in a grid of 5 by 5. So let's do that. And let's hope we get somewhat realistic looking faces. I know they will be weird and creepy, but yeah, they're okay. They're not bad. Sometimes they can be so realistic. You feel like you know that person. But okay, they're not bad. Looks like most of them are smiling, which is good. But my data set, I don't think I have a lot of smiling faces. So, or maybe I do. Anyway, so we know that this is working fine. But now we have to work with, playing with the vectors. So first, let's start by picking 2 random vectors and then interpolating between those 2. I hope one would be neutral, one would be smiling face, so it goes from neutral to smiling. Yeah, we'll see. So that's exactly what I'm doing here. So again, I'm calling this generate latent points. In fact, I could have used this one here. I tend to redefine so it's easier for us to follow in chunks. So first of all, from NumPy, let's go ahead and get linspace. What does linspace do? In case you don't know, you should be, because you should be very good at NumPy before getting into these deep learning topics. So linspace, basically, if I say, okay, between 0 to 1, generate 10 points, it's going to give me 0, 0.1, 0.2, and so on. That's what linspace does, in case you don't know. Okay, so let's go ahead and import that and then generate latent points. And all it's doing is, again, it's going to just generate a few how many of our latent points we mentioned. So in this case, we're going to get 2 random latent points. And then we are going to interpolate between those 2 latent points. So P1 is the first, P2 is the second. Okay. And then how many steps? Like generate 10 of these images between, or 10 latent vectors between P1 and P2. That's exactly what this part is doing. And let's go ahead and do that. And by the way, it's I'm generating values between 0 to 1, like 0, 0.1, 0.2, and so on. And I'm multiplying that with my my latent vector. So in a way, I'm generating a vector that goes from one to the other with a fraction of 0.1 of first vector and 0.9 of the second. So it's like a weighted average as you go between one point to the other. Okay, that's exactly what this interpolate points is doing. And then, of course, another function to just plot whatever we generated. So let's go ahead and define that. Again, I have load model. We have already loaded, but if you haven't, go ahead and load that. And let's generate 2 latent points. Let's hope that they are not close by so we can see a transition in the face. So let's load 2 latent points, and now let's interpolate between these 2. So if you look at our latent points, we have 2 latent points, each of size 100. So let's go ahead and interpolate. Now we should get 10 latent points right there. Each, of course, of size 100. So these 10 are my input to the model. So model.predict with these latent points. We do exactly what we have done before, change the output from -1 to 1 to 0 to 1. And let's go ahead and plot the generated. Let's do this a couple of times in case we don't see the face to be. Yeah, it's going from this type looking face to this. Mouth looks the same. Let's generate a couple other latent points. Yeah, let's generate 2 other random. Let's generate until we are happy with the result. That's a creepy face. It's going from this face all the way to that face. So apparently it's going from lighter skin to darker skin, and some facial features are changing. Let's do this one more time. I just want to make sure it's going from someone with some sort of a weird mustache and beard slowly. And then look at the hair. It still stays pretty much the same right there, but then the face is slowly changing, and it's also adding some smile to the face. So you can see this latent space apparently is a male with some facial features, no smile, in fact very angry, and all the way going to a female looking pleasant face with a smile. Yeah, so that's interpolating between the two latent vectors. But now let's do what we are planning on doing in this video. Do some sort of an arithmetic. So for that, let's come down and define our functions again. We are defining this plot. In this case, I added a save figure so we can open and zoom in rather than see in this tiny box up here. Okay, so and this one also generates latent points, and then let's generate, for example, 100 latent points, generate 100 images, plot it, and then identify certain ones that have the features that we are interested in, and then do the math later on. So first of all, we already loaded the model. Let's go ahead and generate the latent points, and we should have 100 latent points, 100 by 100. Great. And if you are curious how these latent points are spread around, let's go ahead and look at it. Yeah, that's a pretty good spread. I don't want to see random latent points that are close by. So they're going from -3 all the way to 3. Okay, I have some hope in finding a good distribution in our faces. So let's go ahead and run these lines where we are predicting, rescaling from 0 to 1, and then we are plotting it. Okay, so when I say we are plotting it, we are saving the plot to a file right here. So generated faces. Okay, there you go. So you can see these faces. They are semi-realistic. I have a lot of faces with a smile. A lot of faces with smile. I do not have many baby faces. I was hoping to actually take baby faces and do something like an arithmetic with that, but apparently let's actually do. We don't have many faces with mustache either. I thought of. Okay, I'm running out of ideas here. Let's look at glasses. 1, 2, 1, 2. This guy has half a mustache. I don't have glasses either. Okay, I'm not happy with this. So let us go ahead and generate new latent points, predict, and plot. And let's open the plot again. I'm hoping to find something where we can do some sort of an arithmetic. Okay, a lot of smiling faces, which is good to see, but I don't see much of others. So let me pause this video, and then I'll generate a few of these, and then see if there is something that we can use. Okay. Okay, so after spending a couple more minutes, I decided to stick with these: adult with glasses, adult with no glasses, and then person with lipstick. And the reason is, when I generated these faces, I see that to be a common trait where I can find multiple images. So there are a few of these images with glasses. Like if you see image number 3, I start with 1, by the way, counting 1, 2, 3. I see glasses right there. And by the way, let's zoom in so we can see the features a bit better. So there's glasses right there. And 39, so 39, let's go back. 39 would be what, 10, 20, 30, 9 right there. And then we have 40, half glass, or maybe at least we have some glasses there. 50, 60, 61 right there, glasses, and then 86 is the last one I have. So this is 86 right there, so you have glasses. So these are adult with glasses. No glasses is easy. There are many images, so I just picked like 4 or 5. It's up to you how many ever. And then I found a person with lipstick, like you have like 9 and 10. You have some lipstick over there, 11 and 31, so is right here, and 73 right there. So that's the person, and 88 here, some lipstick. So the hope is when we do the math, when you take adult with glasses and subtract adult with no glasses, then you get a vector for glasses, and then you have a person with lipstick on whom we'll put glasses. That's the idea. Okay, again, it's up to you. It depends on the data sets and so on, but with this, that's the best I can come up in this time. Okay, let's go ahead and do that. So we define our adult with glasses as these image numbers. So these are just image numbers. We'll see why we need those in a second. And then I'll give adult with no glasses and then person with lipstick. And you can identify a few others if you want. So I'm assigning, by the way, why did I define these 3, feature 1, 2, 3? Because I play with different features. So instead of changing those names down here, I just assign them to feature 1, 2, 3. So I can do my my stuff down here without, so the only place where I need to work is right here. Okay, now first thing first, we found all of these images with certain trait. You could use any one of those vectors, but then the hope is when you average them, you get a much better representation of whatever that glasses is, adult with glasses is. That's why there is a function here where we are averaging basically the vectors corresponding to these images. Now again, for these images, we started counting from 1, right? So this is 1 to third image, but then in reality, obviously, when you look at your NumPy arrays, it's 0, 1, 2, 3, 4. So first thing first, let's subtract 1 from each of these labels. So this would be 238. If you want, you can directly put 238 and then ignore that line. But anyway, since we have done it this way, this is the line where we are subtracting 1 from the index, from the value right there. And then we'll just go back to our vectors where we have our latent points, and then just look at the whatever that second, like second or 38th or 39th and so on. Yeah, this is how we are extracting the vectors. And once you extract those vectors, go ahead and find the mean. That's it. So let us define the average points, and what would we like to average? We'd like to average the values for feature 1, feature 2, and feature 3. Yeah, and we look at our latent points data, right here. Where is our latent points? We generated 100 by 100 latent points, right? So we are going to look at those. So let's go ahead and average the latent points for feature 1, feature 2, and feature 3. So now we have latent vectors for feature 1, 2, and 3. And the next part is just arithmetic, like we mentioned earlier. Feature 1 minus feature 2 plus feature 3. Again, you can do all kinds of arithmetic. You can enhance your feature 3 2 times and then see what happens. I'm just showing you a simple example right here. So resultant vector, we already got that. Yeah. So let's go ahead and run that line. So now you have the vector that you would like to use as a latent vector to your generator model. 40 minutes later or so, right? Or 30 some minutes later. And let's go ahead and get this resultant vector. Right now, this result vector is just 100. Let's go ahead and reshape it, because the way it goes into our generator is n and the latent vector size. So in our case, n is 1 because we have only one vector. And let's go ahead and do model.predict on this vector. And the rest is pretty much the same as before. Rescale from -1 to 1 to 0 to 1, so we can plot it, and let's go ahead and plot it. Someone with the lipstick with glasses. Someone that has 2 chins apparently, but hopefully you got the idea here. This did exactly what it's supposed to do. It really helps if you have lots of images, because GANs take a lot of images and a lot of time to find a good balance between generator and the discriminator. But what we got here is not bad. Yeah, 128 by 128 size images, almost realistic. Sometimes this is not working out great, but almost realistic, as you can see right there. And if I change some of these, like for example, if I just drop a couple of these vectors, maybe we'll end up with somewhat different type of face. So let's go ahead and do these and see what type of face we get when we run this. Yeah, so our mean changes a little bit. So that's a bit more realistic looking face there. So it depends on exactly what images you're taking or what vectors you're taking and how you're subtracting and all that. So play with this a few more times. That is absolutely a much more realistic image compared to the one where you almost seem like you have 2 faces overlapping there. So this is at least one realistic looking face with glasses and lipstick like we intended. Okay, I really hope you don't find this to be boring. In fact, I hope you found this to be very useful. And please go ahead and hit the like button if you really like this video. And of course, as usual, I request you to subscribe to this channel, which always keeps me encouraged to create new content. Thank you guys, and let's meet again in the next video.